All right. Yeah, good afternoon. I'm planning on doing a brand new leak code problem that I found and share my screen here real quick. Let's see. Hold on one sec. Okay. So this is one of the questions you have to pay a little extra for, and that it's locked if you don't have a premium subscription. By the way, I think the leak code premium subscription is totally worth it. I think it's super cool to support these folks and what they're doing. It's awesome to practice coding algorithms and data structures and seeing some other folks and how they did it. But anyhow, yeah, so this is what I plan on doing. Is this new one, which I have unlocked since I pay for this thing. So let's go here. Okay, and yeah, I can do this one in Kotlin, whatever. So you're given two zero index integer arrays the same length, present and future. Present I is the current price of the I stock, and the future I is the price of the I stock in the future by year. Okay, and then you buy each stock most once. You get an integer budget representing money amount. Okay, maximize the product. Okay, cool. This one looks like dynamic programming. So let's see if some of the dynamic programming work I've been working on pays off here. It's a challenge, I think. Here's the game plan though. All right, so keep trying to check out how many minutes it takes. Coming up with game plan. All right, so we are maximizing the profit. That's our objective function. Right, so our current choices may affect future choices. So we want to, excuse me. There we go. Yeah, so current ith choices affect future ith choices. So we want to optimally choose. Right, thus we are formulating future from the past. So here's the thing about dynamic programming. If you forget the past, you don't remember the past, you're bound to repeat it. So we use memoization of depth first search, top down, basically considering all possibilities, memoizing the ones that we've already solved previously and building upon those. And then we'll turn it upside down. So basically I'll do the ART of art, right? All remember and turn. So that turning part is the hard part because we have to explicitly specify the base cases before they're iteratively built upon, whereas the top down allows us to implicitly have the base cases when the recursive stack bottoms out and begins to unwind. So anyhow, let's go through this. Right, our choices are either we include or disclude each item, right? So either we're gonna buy this one and sell it here, or we're not gonna buy it or sell it there. So this is like a 0-1 knapsack algorithm, basically. For each stock, we have two possibilities to explore. One include, two is exclude, right? And then yeah, we put like a little picture here. Exclude, no, just something like that. And then like a little green checkbox for this guy. Okay, so let's just do A, B. And this is what we have. All right, so we can profit that, I guess profit occurs. X is equal to A sub I minus B sub I. Right, notice if I guess profit, right? Profit only exists when a sub I is greater than b sub I, right? So buy, no, b sub I is greater than a sub I, right? So we buy at A and we sell at B. Also, we also have to track. We also track how much money we have. Okay, yeah, so that's the game plan. So 2:08 to 2:12 p.m., about 4 minutes for the game plan. And then let's start the implementation here and see what happens. Keep track of how many minutes for implementation. Okay, here we go. So we can just zip these things and then call it profit, right? So let's do that. Our profit equals a zip b. Not sure if that syntax is right or not, but it's something like that in Kotlin to zip the two integers arrays. Or actually, we just call it. Actually, no, we'll calculate the profit, right? Or wanna. I don't know. Let's do this. Let's just call this thing B, call this thing C, and we'll zip it as A, right? A is A zip, B is C. Right. So we'll just have A as pairs, first and second. And who knows if this is right? Actually, I'm not going to do this in Kotlin. Never mind, right? I'm going to take this. I'm going to just do it in JavaScript. JavaScript's like super flexible, whereas Kotlin's kind of a pain for some of that stuff. Let's do this, right? When we use Lodash, just do the zip. Hold on. This guy's B, this guy's C, and this is how much money we have. And then we'll do A equal underscore dot zip B C underscore is Lodash, right? Okay, and then we'll return our best at the end. Right, so we're gonna recursively consider all possibilities. Go equal start at I. How much money do we have? I don't know if you want to call this thing. I'll just call it budget, whatever. Budget here, and then I have is what our budget is. Budget initially, right? Okay, that looks good. So if I is equal to n, which is length of A, that's going to be our base case, return 0. So as the recursive stack unwinds, we'll optimally return the best profit we can make. So either include or exclude. If you include it, then we have to have enough money to include it. So let's include will be cost is, hold on, let's do this. That cost to take it into, or I guess to buy and sell, right? Buy, sell is a sub I destructured, right? If we have enough to buy it, right? So have is less than or equal to buy, then we can buy it. We wouldn't want to ever buy it as a loss, but whatever. Anyhow, to profit equals buy, sell minus buy. If we have enough to buy it, right? Buy is, oh no, have should be bigger than buy is, right? We have enough to buy it. Then we have profit plus go I plus 1 and minus phi. Otherwise, if you don't have enough to buy, I just do infinity, which is a case we never want to consider. Otherwise, if you exclude, just go I plus 1, whatever we have. And then we'll return the maximum of including and excluding. All right, okay, so that's the basic thing. There's our budget. If we have to buy, oops, negative infinity here. Actually, want to maximize our profits. A is that, so that, right? And we can clean this up a little bit because it's kind of ugly, but whatever. For now, first pass, this seems pretty decent. Let's see what happens. Okay, that's cool. And then let's do the other test cases. So it's 650, looks good. Okay, so I'd expect this thing to TLE, right? So TLE without a memo, and if memo is a top down, then it should be accepted. Map. Okay, cool. So it's TLE, right? So this is 2:17 p.m., about 3 minutes for the implementation for top down, which results in TLE 218. Add a memo. It shouldn't take more than a minute for implementation. Adding memoization, right? Here we go. So there's our new map, and then let K be our key, which is I have. The map does not have that key, then we'll do this, and then return that in the end. Right, so set our key here. Okay, there's the memoization, and big money, no whammies. It's going kind of slow. Okay, cool. All right, so that was an accepted solution. That's less than a minute, so that's cool. All right, less than 1 minute with implementation, memoization, top down, and then the most difficult part, I think, is probably going to be this turning it upside down and then seeing if we can do a memory optimization or something like that, right? See what the current row, yeah, so the current I choice is dependent on the previous I minus 1th choice. There is memory optimization, which could be formed. Yeah, so let's do this next. Okay, do the turn part, turn the top down solution upside down to formulate the bottom up solution, right? Okay, so I want to do DP is an array of the base case at n, your base case, and then all the different values that we have, and then we'll bust out the profit at the end. We're simulating the recursive stack unwinding. DP sub 0 in our budget. That's what we have. Okay, so map this thing to what we have plus 1, right? So actually, this is our budget. Let's call this thing half. Whatever. I'll just keep it. Try to keep it consistent. Whatever. We'll clean it up later if we want to. Map. I want each row of that to be mapped to an array of size budget plus 1 for 0 to budget inclusive to fill with negative infinity. And then set DP, all the values sub in our base case, right? So let's do this. Let for I equals 0, I is less than n. So this is part of the difficulty of dynamic programming bottom up, is that we have to explicitly state the base cases. Like it can't just be implied by the base case of the recursion bottoming out. So here we're explicitly specifying from I equals 0 to n inclusive. We're going to set dp sub I sub. Oh wait, so all the budgets in, right? So we want this guy to be in, and we want all budget values, right? So this is the base case, which would pretty much be this part, right? So for all the different budget values, we'll set that. Right, so we have, okay, so let have equals 0, have is less than or equal to budget inclusive. All right, so all those is the base case that we have. Then we were iteratively build upon that base case backwards as the recursive stack on lines, iteratively and optimally choose best choices to maximize the profit. So for I equals n minus 1, I will go down to 0 inclusive. And for let have equals budget, I'm going to go down to 0 as well. Or actually, hold on, we want to build previous, so we want to go the other direction, right? We want to build upon the solutions. We had less money, and as you have more money, then we'll do that. We want to go, well, if you have nothing, you can't afford anything, right? I don't think it'd take, does anything have a cost of 0? Well, maybe it does cost you 0, and then you can sell it for something. Okay, well, anyhow, all right, so we start at have is, oops, hold on, have is, what's going on here? Nice. Go this way because we want to build upon have is less than equal to our budget at the end. So that's the way we want to go. So the recursive stack can win that way, and then we have this way. Okay, that looks right. Now, okay, so we'll do the same thing as the top down. Basically, the logic is no different. We zip that, buy at this price, you sell at that price, we destructure it here. So our profit is what we sell at minus what we bought at. Include is then if buy is let's make sure what we have. We profit plus dp sub I plus 1 have minus buy. So basically this is like the knapsack, right? Right, 0, 1 knapsack algorithm. Exclude, which is pretty cool, by the way. You know, I want to take a break and mention this while it's on the top of my mind. This is cool because it is a computationally intractable problem which compromises on generality in favor of correctness and speed. That is, we can, when we deal with computationally intractable problems, we can only deal with them in polynomial time, like a reasonable amount of time, not exponential time, if we choose 2 out of 3, right, out of generality, correctness, and speed. So this is cool because many of the leap code problems, Q4 problems, do compromise on generality in favor of correctness and speed. So, okay, that's my side shoot, but let me get back to this, right? Let's focus our DP, so but this is exclude I plus 1, what we still currently have. Right, so then DP sub I is dependent on DP sub I plus 1, right? We'll just take maximum of those 2 choices as the recursive stack is mimicked to be unwounded, exclude, right? And DP sub I, what we have at that stage. Okay, so let's see what happens. Okay, cool. Yay, all right, so I think maybe a little bit of what I've been practicing for the last 4 years is paying off a little bit. And this is really tough stuff. I think it's not easy for sure. We're not using this map, so I'll delete this part. But anyhow, let's do the memory optimization, and then I'll jam on this in the other languages and see if some of it sticks, see if I can do it a little bit faster. And if I can do this faster, which is super cool, is I'll be actually a contestant, not just a participant in the contest. So I'm totally stoked to try this out tomorrow morning. I plan on joining that contest. Okay, so anyhow, let's do this. Let's formulate the current row based upon the previous row. And basically we're going to do the memory. Oh, by the way, let me see how much time this took me. Oh, I didn't write down how much time that took, but I finished at 2:27 p.m. So if we started at 2:18, let's assume I started up there, 2:18 p.m. to 2:27 p.m. It's like 9 minutes, right? 9 minutes for implementation, which results in AG. Yay. Okay, now it's going to be 2:27 to, I don't think this will take too long, whatever it is, for how many minutes for the implementation of the bottom up memory optimization. Okay, so formulating current from previous based on row by row. So that previous row will be, each ith row is of size budget inclusive, array budget plus 1 fill. That'll be our base case. So we don't have to do this explicitly. And then we'll formulate current from previous. Like current equal an array of size budget. Plus 1 inclusive, which will fill with infinity. Okay, and then basically we're going to replace current with previous, and then whenever we have d piece of I, this is basically current, d piece of I plus 1 is previous, since we're going from the right to the left. Those are the relative offsets. All right, so current, what we have is based upon the previous solution of what we had. Okay, and then we're going to swap current and previous, or current will equal, let's just do this here, current, or previous equals current, right? That's what we're doing. And then in the end, we're going to return previous given that budget. Okay, looks good. Yay, okay, cool. So that took 2 minutes, 2:29, 2 minutes. Okay, awesome. So well, there you have it, right? So we had started off here, right? These are all the possibilities that we have, either include or exclude each ith stock, and there's profit made when we can sell at a larger value than what we can buy it at. Actually, this is B minus A, right? Or we call this thing C and A, but whatever. I wonder if I want to clean that up a little bit. If I want to zip it differently. So let's consider cleaning up this code before I duplicate this in basically every other language I've been practicing. So yeah, instead of doing this, we could say this is buy and this is sell, right? And then profit would be sell sub I minus buy sub I. And this does make it a little bit easier, I think, right? I mean, why do I need to zip the thing? It makes no sense. And yeah, that looks cool. All right, okay, so oops, dot length, be buy dot length. N is only used once as well, so whatever, it's fine. Whoa, that's not right. Something's not looking good here. Oh, it's actually, so wait, yeah, so that sell sub I minus buy sub I. So what's going on here? Why is this returning 0? 0 would mean there's like no profit to be had. Buy, sell, right? Sell, minus buy for each I. Oh, this guy. So what we have, okay, so bi sub I has to be less than what we have minus bi sub I. Okay, yeah, so that looks good. Okay, cool. That looks decent enough code, right? This is our profit. Actually, just stick that there, right? This is for our profit. Nice profit. Yeah, that looks okay. You don't want to be too verbose with a whole bunch of different variables, right? So let's do this. The art of dynamic programming. I'll stick it on this guy. And this in the subject. Boom. Link to that guy. And hopefully this helps folks, because I had a really hard time learning this basically from scratch. I had to find this out on my own. And the reason I do this is because a lot of people still post their very last solution. Like if I do all this work and then I post this last thing, like a super concise memory optimized solution, who does that help? It's very it's very discouraging, because I didn't jump straight there, and you might think that if that's the only thing that I posted. So yeah, I'm not here to be like a super smart guy or anything. I'm just trying to learn and do my best, So if y'all think this is helpful, then that's awesome. That's what it's here for. Okay, so grab I'll grab these guys that are already formatted. Hold on, where is it? This guy. Grab this. And basically, I'll do this for all the languages, right? So I did it first in JavaScript solutions. And I'll post these guys and then do it in the other languages and post those too. Okay, and then the floor is memory optimization. The current row is dependent on the previous I+1. Row. All right, so basically dp sub I will be current, dp sub I+1 will be previous. Okay, cool. So here we go. Copy and paste these guys in here, and then I might as well just practice writing these over again. And whatever. I don't think it take too long. I'll just, based on this guy, I'll write them all about the same, right? So add a memo. And is our new, new map. Okay, and then key will be so those are variables that keep track of our state. If the map does not have the key, then we'll compute that subproblem solution once and store it for future lookups. Okay, and then return look at that key. Oops. Okay, so this should be accepted. Okay, cool. And also, we should look at this. Look at the runtime of this top-down solution compared to bottom-up. Bottom-up is way, way more faster. Way, way more. Anyhow, okay, let's stick this here and do the bottom-up, and then do the bottom-up memory optimization. So basically, we're mimicking the recursive stack unwinding explicitly. let's get rid of that order. So let's TP equals array of n plus 1, which will map each row to an array of budget. This one's for 0 to n inclusive and 0 to budget inclusive, and we'll fill these negative infinity. Explicitly state the base cases. All right, so our budget of what we have 0 to this is our budget inclusive. Right, so DP sub n, which is our base case, when we have 0. Those are explicit base cases, which we iteratively built upon. So iteratively build upon them, then we're going to go I equals n minus 1 and down to 0 inclusive. And then we're gonna go with what we have beginning to our budget inclusive and iteratively build upon those base cases optimally and return this budget. Okay. So actually, let me just copy and paste this guy here. I don't need to type this all over again. My fingers are going to start getting tired. Basically, instead of go, right, we're just using DP. So this guy, so that guy. And then likewise here, we're just explicitly using our DP state as we mimic the recursive stack unwinding. Oops, include or exclude. Exclude. Okay. Oh, DPI and a half. Okay, that looks good. Yay. Okay, and then do the memory optimization, and then we'll do it all over again. Let's start all over in all the other languages. We pound it in there. I'm in it to win it. You know, I want to win a LeetCode contest. That'd be awesome. Okay. So we will use previous. It'll be an array of budget 1, which will fill with 0 as our base case initially. So we don't need that part. Add current is an array of budget 1, fill with our worst case scenarios here. All right, and then I plus 1 is previous, since I plus 1 is before I, as we go from right to left. That's the relative offset, just with current, and then say previous plus current, and then return previous based on our original budget at the end. Okay. Looks good. Cool. All right, there we go. And boom. Okay, JavaScript is cool. So let's just do this in Kotlin. And next, let's do this and put some placeholders here. Delete this code. Okay. Just copy and paste these before I start jamming again. Okay, so these will be my Kotlin placeholders. Kotlin, JavaScript to Python 3. Oops, Python 3. I don't think I want to do Rust. Rust, I still haven't found out how to create a recursive Lambda or recursive closure in that I want to capture the global variables, so I don't have to pass them in as parameters to the function itself. It's a huge pain. It's very verbose and redundant, I think. Anyhow, okay, so this is the game plan, right? Python 3, C++. We already did JavaScript, and then we'll do Kotlin next. All right, here we go. Let's do Kotlin. Okay, here's my original game plan, and then I don't need this, right? This is buy. It's gonna sell. This is the amount of money we have. N is by size, and we're gonna return and go in the end here. It is fun to go. And then have will be an integer equal originally to our budget. We'll return an integer in the end. So if I is equal to n, this is our base case, we'll return 0. The recursive stack bottoms out there and begins to unwind. And then we have two choices, right? So we can include, which would say, if we have more than what it costs to buy the ith item, if, then we can say sell sub I minus buy sub I is our profit plus go I plus 1, have minus buy sub I. Otherwise, we just say it's infinity, which we can just make as a large number. 29 plus 7. Oops. Works. Negative infinity. Exclude would equal go I plus 1 and what we have, and then we'll return the maximum of those two choices, include or exclude. Okay. Uh-oh. Budget. Okay, let's go budget. Budget. Okay, so this guy should TLE, right? Okay, so I think it's really 2:43 p.m. Okay, so that really is that? No, I didn't start at 2:12. I don't know what time I started at. Whatever. Yeah, I don't think it took me that long though. Okay, so that'll TLE. Stick this guy here, and then add a memo for AC. Hopefully, big money, no whammies. Here we go. RM is a mutable map of which is strings for our key, right? And our state is I, and whatever we have. If the map does not contain key, then we'll compute this once and store it for future lookups. Okay. Uh-oh. Mutable map of, oh, it's string to integers is what the mapping is. And not contains. Okay, that looks good. And I expect this to be accepted. Big money, no whammies. Come on. Oh, it's still too late. Okay, so. Huh. Yeah, it looks okay. It looks right to me. Whatever. Let's flip it upside down. All right, turn this thing upside down, and basically we're going to do this. Turn GPU sub 0. Set the original budget, which should be optimally the best that we can do. Right. Okay, so DP is an array of size n plus 1 for 0 to n inclusive, and we will have integer arrays of size budget plus 1 for 0 to budget inclusive, and then we'll explicitly set the base case for what we have 0 into budget inclusive. DP sub n sub have is 0, and then we'll iteratively and optimally build upon that from the bottom up. I and n minus 1 down to 0 for have and 0 until budget inclusive. So we're going to say include is if cost of buying the item is less than or equal to what we have, then it'll be, we can sell that minus what we bought it at plus the previous state of what we had without like that amount of money. Otherwise, say negative infinity. And then exclude is the state of what we had previously. dp sub I is equal to the optimal solution of what if we include it or exclude it. Okay, that looks right. Or dpi, oops, I have. Looks good. Yay, okay, cool. Accepted, and then let's do the memory optimization. We'll jam on this in Python, C++, and call it a day. Or like call it a day for this problem, at least in this video. All right, so let's go. Let's go. Come on. Our previous is an integer array size budget plus 1. We'll set to 0 as our base case here. Explicitly set. That's cool. Current is an integer array budget plus 1 size, which is initially set to the worst case scenario here. And then we want to replace dp sub I plus 1 with previous and dp sub I with current. Current and then previous equals current. And then we're going to turn this guy at the end. Okay, looks good. Bam, cool. There's Kotlin, so Kotlin JavaScript, and let's do Python 3 and C++. Here we go. All right, I'll put the clock here, 2:48 p.m. to however it takes here. Okay, so this guy's a buy. This guy will be our sell. This is our budget. And n is the length of I. We'll keep our state. I is initially 0. Have is initially budget. If I is equal to n, then we'll return 0 as our base case. Otherwise, include is have is if I sub I, so let's think about have as negative infinity. Let's do this. All right, actually, now let's do 29 plus 7 is cool. Negative infinity. Okay, so that'll be what we can sell it at, minus what we buy it at, the item is what profit, plus go on to the next plus 1 option, which have minus what it costs to buy it. Exclude, then it's the easy part, plus 1, we continue to currently have, and then we'll return the maximum of including and excluding it. Exclude, okay. Go. Okay, so that's that. That's cool. Okay, and adding a memo on Python is super easy. So this is about 2 minutes, right? 2 minutes for implementation in Python 3. And I expect it to be accepted with a memo. Let's do this here. All possibilities. It's our memo. It might TLE, I don't know. Let's see what happens. It depends on how strict the online judge is sometimes. Yeah, okay. Whatever. This one TLEs, but if we turn it upside down, then it should work okay. As it turns this guy upside down, P equals infinity times budget plus 1 inclusive, and we'll have that many rows. 0 to n-1 inclusive rows. So Python's a little bit weird sometimes in that you write things backwards, like you read it backwards, like these are the rows and then these would be the columns. Yeah. Naturally, I think we think from left to right rather than right to left. Same thing with the ternary operator, right? So if the if statement is true, then we do this part in the beginning, which it does have some of its advantages. Like we could go up here so it aligns right here, and we could do plus this guy over here, which is kind of nice. You can see it in lines, but it doesn't really matter. It doesn't have to be perfect. Okay, let's move on. Let's get going, right? So we're going to turn, this is the topmost recursive call, 0 in budget. And then we're going to mimic the recursive stack unwinding based upon the base cases, which we need to explicitly set for have from 0 to budget inclusive. So for have in range 0 to budget, it's one inclusive, let's say dp sub in sub have is equal to 0, and then we'll iteratively optimally build upon that. So for I in the range n-1 down to -1 non inclusive by -1, we will do for have in range 0 to budget +1, budget inclusive. Include is profit we could have if what we buy at, say we have when the cost to buy it, then we can say profit is what we sell at minus what we buy at plus dp state of I+1. So we have minus what it costs to buy it at. Otherwise, negative infinity. We don't want to choose that option if we can't afford it. dp sub I+1 and what we have in the previous state. The dp sub I is simply the maximum of those two choices. Okay. dp sub I have, right? Okay. Uh-oh. There we go. Wait. So no. What is wrong here? What did I do? For for that in range. Okay, that was good. Big money, no whammies. Okay, cool. That guy's cool. And then before we move on, let's do the memory optimization since the current ithrow is only dependent on the previous ithrow. All right, so previous is this guy. Oops, hold on. Yeah, that guy looks good. Okay, that's previous. And then actually we want base case there. Okay, so then current is worst case times budget +1. And then replace dp sub I+1 with previous. It's gotta be current. And then turn this guy at the end. Okay, that looks good. Uh-oh, that is not good. What did I do wrong here in previous? 0 times budget +1, negative infinity times budget +1. Oh, wait, hold on. Previous, yeah, that looks right. Previous. Oh, I didn't set previous equal to current. Okay, there we go. Looks good. Big money, no whammies. Yay. Okay. It sure does take a long time in Python compared to the other languages. Okay, and then let's do C++ next. Okay. Water break. Okay. Oops. Vector in. So we'll just clean this up a little bit. Okay, leave that guy there. Behind by. So, okay, fun. It is fun to go. Capture go in your own recursive lambda. All right, return an integer, taking it into state. That is the ith choice, and what we have is our budget. Oops, so what do I have? All right, return go 0 budget. If I is equal to n goes by size, it's the cardinality of the array. So that's our base case. Include is if we have enough to buy it, tries to buy, has the cost of that. We have enough, then we say we sell it at minus what we purchased it at, plus have minus what it costs to buy it. Otherwise, infinity. Let's do this at 7. All right, there's include, and the other option is to exclude. Exclude is just simply go into the next item with what we have, and we'll return the maximum of include and exclude. Okay, that looks good. Boom. Add a memo. And it may or may not TLE. It really depends upon the online judge. Right. This guy. Okay. And then we'll create our key. Just on a hash. It's just a key. This is our state, which we need to memorize. So our string to on and oops, and turn that guy in the end. Okay, then K is our key. I have if what find a key is the end of the map. Right, we'll compute the solution once and store it for future lookups. Okay, that looks good. Oh, string. I didn't mean that. String. Uh-oh. String. What? That operates a binary expression. Really? String. Oh, oops, it is the wrong direction. Stick it into that thing, right? Don't get it out of that thing. All right, okay. All right, that looks good. Okay, let's see if it TLEs or not. Maybe it will, maybe it won't. It's all up to the OJ. Okay, online judge says no, it's not fast enough. Let's turn this thing upside down. All right, here we go. Turn it upside down. We don't need our map or our function. Explicitly mimic the recursive stack unwinding. Okay, so using VI, vector, vectors, VVI, DP of size n+1, budget +1, and we're going to initialize that all to infinity, and then for we have from 0 to budget inclusive, explicitly set the base cases at n to what we have to 0, and iteratively and optimally build upon that from bottom up. Budget 0, budget here, end. Okay, now 0 to inclusive to code equals, if we have what it costs to buy it, we can buy it. We'll see the profit is, we can sell it at, and that's what we bought it at, plus TP sub the state of the previous without the money that it costs to buy that thing. Otherwise, definitely, if you cannot afford it, we don't want to even consider that option. Include is simply the previous state with what we have. Okay, and then dp sub I, which is current based upon previous, is the maximum of this previous two choices. Okay, oops, I and a half. I keep forgetting this part. It's exactly getting that. Okay. Oh, what's going on here? Addition onside offset in in should be an integer. Okay, that's good. Yeah, it's always sketchy to be subtracting one from a unsigned integer. Remember a fellow. Never mind, I'm not going to talk about anyone else. Anyhow, don't subtract -1 from unsigned integers. So just make an integer. It's way safer C++ code, which you want to be very careful about. Okay, anyhow, let's do this one, the memory optimization. Okay, so VI previous is of size n, base case is 0, set, which we will iteratively and optimally build the current upon. Okay, and then basically just replace dp sub I with previous. dp sub I, or dp sub I plus 1 plus previous, and dp sub I is current, and then current is previous is current, and then we'll return this guy at the end. Uh-oh. Let's see what happened. What did I do? Oh, it needs to be n plus 1. So it's n plus 1, n being inclusive. Well, that still didn't work. What happened here? Oh, wait, it's not n, it's budget. Oops. Right, there's n rows, but then the column size 0 to n, not to budget inclusive. Right, that was good. Okay. All right, so obviously I'm making some simple mistakes and it's time to take a break. That's a lot of coding. My fingers are kind of tired. Right, so there you go. All right, to start off the top down, memorize it, and turn it upside down, and then do the memory optimization. So let me just grab, copy this guy again. Just stick it up top for reference. And then the fourth one is just the memory optimization. Boom. Okay, so there you go. Hopefully it's helpful. I really wish I had this when I first started learning DP. Just keep things like super simple rather than trying to show off how smart I am, right? So I'm here to learn, here to help folks, not here to be super smart, know-it-all guy. And hopefully it comes off that way. I think that's legitimately helping folks. Yeah, so this is cool. All right, yeah, so yep. All right, and catch you next time.